Hello, everyone. In this series of Science versus Jehovah's Witnesses, we'll discuss radiocarbon dating, how it works, and why it is considered by researchers as being reliable. First, let us discuss how radiocarbon dating works to begin with. Carbon exists in three different isotopes: carbons 12 and 13, which are stable, and carbon 14, which is radioactive. Carbon 14 is normally produced when cosmic rays produce free roaming neutrons in our atmosphere, which in turn reacts with nitrogen atoms by exchanging itself for a proton, therefore changing the nitrogen 14 atom into carbon 14. Once formed, it reacts with oxygen to form carbon dioxide, which is then absorbed by plants through photosynthesis. These plants are thereafter fed upon by animals, which are in turn fed upon by other animals, and so on and so forth down the food web, constantly replenishing their carbon 14 intake until they die. Carbon 14 has a half-life of 5,730 plus or minus 40 years and decays into nitrogen 14 through beta decay. The ratio between carbon 14 and carbon 12 in our atmosphere, being around 1 part per trillion, is consistent enough to make carbon 14 useful for dating applications. By counting the remaining carbon 14 atoms left in the sample, then comparing that amount to the stable carbon isotopes of the same sample, researchers can then work out when the organism which produced the sample died. Two methods exist for measuring the amount of carbon 14 in a given sample. The first method was beta counting, which simply counts the amount of beta decay by weight within a specific span of time. The second, now favored technique, is by accelerator mass spectrometry, which directly measures the amount for each isotope. In a perfect world where all factors are constant, a calendar date can be determined for any given sample. Unfortunately, this is not the case, as multiple known factors can affect the dating results. First, the amounts of the different isotopes tend to fluctuate over time, and therefore the ratio between carbons 12, 13, and 14 are not constant. Second, plants undergoing photosynthesis tend to favor the lighter isotope carbon 12. Likewise, they also favor carbon 13 over 14 to a small but measurable degree, indicating that the carbon composition of plant material does not accurately represent the carbon composition of the atmosphere. This phenomenon is called fractionation. Third, organisms that live in freshwater and marine environments draw some of their carbon from places which had already depleted its radioactive carbon. This gives the organism an older apparent age than it really has. This phenomenon is referred to as the reservoir effect. Fourth, the size of the sample is important. Since radiometric dating relies on the law of large numbers, a sample that is too small can give inaccurate results, especially if the sample is really old, with very little carbon to detect. In the days of beta counting, a 10-gram sample was required. Now, with the more sensitive approach of accelerator mass spectrometry, a sample as small as half a milligram could be used. The size of a given sample can also determine the dating capacity of older samples. At times, a larger sample can push the dating capacity from 50,000 years to around 70,000 years. If the sample is any older, carbon dating cannot realistically be used, since there is often so little carbon contained within the sample that it makes significant detection very difficult. To resolve these issues, a database is created made up of independently dated samples archiving 55,000 years worth of carbon 14 fluctuations. Tree rings, for example, bear sequences of annual rings which can be cross-dated with other sequences from previous generations, going back 13,900 years. Since trees only give nutrients to the outermost ring, each ring is a time capsule preserving the amount of carbon 14 in a given year. Other pieces of data come from other sources, such as the Lake Suigetsu sediment layers, or varves, stalagmites from Hulu Cave in China, ocean corals, and other pieces of data aid for a higher resolution of the carbon 14 record going back 55,000 years. This database forms a useful plotted graph known as a calibration curve. The most recent addition is InCal 20, which was published in 2020. This calibration curve enables researchers to use the uncalibrated radiocarbon age of a sample in order to give a more precise age estimate. What's interesting to note is that according to the calibration curve, the uncalibrated radiocarbon ages tend to underestimate the real age by a few thousand years in most places on the curve. This stands in stark contrast to the claim made by Jehovah's Witnesses that the radiocarbon ages tend to drastically overestimate the real age of a sample, since they often contradict the main narratives of the earliest portions of the Bible. In part 2 of this video, we'll discuss some of the main objections made by Jehovah's Witnesses about radiocarbon dating. Until then, keep on keeping on.